First thing I wanted to mention was this is something I think Hussein posted in the Slack. This is from Stephen Wolfram's blog. Um, and, he's interested in a lot of sort of applications of physics to science, but also a lot of stuff with AI and applying AI to doing science. So, this is an article, though, where he talks about brain size, and it's what if we had bigger brains, imagining minds beyond ours. And so this is kind of related to the connectome stuff we talked about earlier, but also kind of thinking about how do you expand your mind using technologies to expand our minds. So um, he talks about he starts off this article with the subheading "Cats Don't Talk." So we humans have perhaps 100 billion neurons in our brains, but what if we had many more? Or what if the AIs are built effectively had many more? What kinds of things might then become possible? At 100 billion neurons, we know, for example, that compositional language of the kind we use as humans is as a possibility because we do this. At 100 million neurons, that at the scale of a cat's brain, it doesn't seem to be the case. So cats can't build compositional language, but we can. And one way to view that is it's a difference in of scale. So when you have 100 million neurons, you maybe can't do compositional language. At 100 billion neurons, you can. And I say, it appears to be because, first of all, we don't know what cats use in their own minds to process the world. We know how they can communicate. They don't have language, but is that they don't have the capacity or they just don't have something else? Which, of course, brings us to the other question. Is it all about the number of neurons you have, or is it something else? So we know that basically the number of neurons scales to the number of connections. So, as we saw in that table when we were talking about the connectomes, the more neurons you have in general, the more connections you have. Well, what if it's something else? What if it's some other sort of representation or some other form of capacity in the brain that or in the connectome that is important? So that's, kind of a question that he's setting out here. My purpose here is to start exploring such questions, informed by what we've seen in recent years in neural nets and large language models, as well as what we know now about the fundamental nature of computation, about neuroscience, and the operation of actual brains. So this is a table here where he talks about these different numbers of connections at different scales and what they can do in terms of behavior. So remember, again, we had that table of, in the brain emulation white paper, they talked about different numbers of neurons, different connections, and being able to emulate them at some meaningful scale. Here he's talking about if you have a number of connections, perhaps in a neural network, where it's not a connectome, but it's just kind of a layered, randomly connected network that gets, weighted by learning from data. What kind of behavior can be generated from a network of a certain size? So this is around 10 to the 5th connections. We see recognition of images of 10 digits. So this is where we have like our MNIST data set where we can learn that effectively. At 10 to the 6th connections, we can recognize images of all letters. So again, this is like, again, the MNIST dataset level type learning. At 10 to the 7 connections, we can recognize images of 5,000 picturable nouns. So we can do very basic language processing at that scale, at 10 to the 7th connections. And remember, as we go up in terms of our exponent, this gets exponentially larger. So, 10 to the 6th is a million, 10 to the 9th is a billion, and so forth. So we're really increasing the number of connections here. And then at 10 to the 8th connections, We can transcribe speech from audio. We can do sort of multimodal processing and multimodal conversion. At 10 to the 9th connections, we can generate photorealistic images from text. And then at 10 to the 11th connections, we can generate fluent natural language text. So this is the large language model. So again, this is this compositional language at 10 to the 11th connections, whereas, at smaller scales, we can't do that. So this is kind of the argument that the kinds of breakthroughs we see in neural nets map to the brain. And then the question is that really the way that brains work? Well, I don't know. But we definitely have these capabilities, and so maybe one argument is that it's about, brute force connectivity. In other words, if I have just enough connections, I can do this sort of thing. I can have compositional language processing. But it might be true that you could have another architecture that's much less, requires much less capacity to do a similar thing. It's not really clear. I mean, it's interesting that he didn't bring up birdsong and birdsong production, because birdsong production doesn't use as complex of a circuit in terms of a human speech. It's similar to the human speech pathway, but it doesn't involve as many neurons to produce basically a compositional language. So I don't know, but in any case, so what's next? No doubt there will be things like humanoid robotic control that have close analogs to what humans already do. But what if we go far beyond the 10 to the 14th connections that our human brains have? What qualitatively new ideas of capabilities might there then be? If this were about computation in general, then there wouldn't be really much to talk about. The principle of computational equivalence implies that beyond some low threshold, computational systems can generically produce behavior that corresponds to computation that's as sophisticated as it ever can be. And indeed, that's the kind of thing we see both in lots of abstract settings and in the natural world. But the point is we're not dealing with computation in general. We're dealing with the kinds of computations that brains fundamentally do. And the essence of these seems to have to do with taking in large amounts of sensory data and then coming up with what amount of decisions about what to do next. So there's this aspect of, the stuff we've been working on with respect to Gibsonian information and Gibsonian learning and things like that. That's, he's pointing to that and saying, look, there's sensory data, it's coming in, and then, we're generating these behaviors at a certain threshold of some architecture. So I think it'd be interesting to revisit Gibsonian information in terms of this statement. It's not obvious that there'd be any reasonable way to do this. The world at large is full of computational irreducibility, where the only general way to work on what will happen in a system is just to run the underlying rules for that system step by step and see what comes out. And he shows a picture of the output of a cellular automata program. And so what's interesting about this is that he's saying that you can't reduce this to specific connections or maybe even specific interactions. You have to just have maybe a system of rules and then a generative process that's forward, but you can't reverse engineer it. So you have to just let the program run and see what it produces. And then you know whether that system has the capacity to produce, say, computational or compositional language or some other complex behavior. And so this is, kind of talking about some of the things they've done with large language models and some of his cellular automata models and such. So this is a nice article. It kind of talks about the brain and how, do we have a single brain, but maybe we have a single brain with sort of different emergent concepts. And I think, that paper Beyond Networks, I found that interesting when Jesse posted that in the Slack, because it's kind of hitting at some of these same issues that there are these different types of emergent structures in the brain or emergent features of a connectome that kind of define maybe what we're talking about as intelligence. He talks about here, he gives an example from dogs. He said, what if there's a bigger brain with more emergent concepts inside? To communicate about them at a certain level of precision, we need to use more words, if not a fundamentally richer form of language. So if you think about dogs, they understand isolated words, and with our larger brains, we can deal with compositional language in which we can construct an infinite range of meanings by combining words into phrases, sentences, etc. And then, but at least as we currently imagine it, language defines a certain model of the world based on some finite collection of primitives, such as words and concepts. And so, in this sense of computational irreducibility, though, we know that such a model can never be complete. Instead, the model has to approximate things based on a network of pockets of reducibility that the primitives in the language effectively define. And insofar as a bigger brain might, in essence, be able to make use of a larger network of pockets of reducibility, it can then potentially support a more precise model of the world. So this is, he talks about this kind of incomprehensible and irreducible computation that's characteristic of so many abstract systems in nature. But it could also be that in being a brain-like construct, it necessarily tap into computational reducibility in such a way that with the formalism and abstraction we built, we still meaningfully able to talk about what it can do. So this is really interesting, talking about kind of the possibilities of intelligence in bigger brains or smaller brains and what that means. The other thing I want to talk about is this article. So the other thing I want to talk about is this. This is from Maxim Raginsky's blog, The Art of the Realizable. And this is Hayek's Abstract Logic 9000. And if you're familiar with Hayek or Friedrich von Hayek, he has an interesting take on cognitive science. Of course, he's known as this guy who wrote The Road to Serfdom and a lot of sort of libertarian tracts, and sort of one of the main neoliberal precursors. And so that's kind of where he's coming from. But he also had a lot of interesting views on cognition, especially in terms of very embryonic connectionism and how, we think about connectionism as this sort of emergent phenomena. So we think of connectionism as sort of emerging from different connections or emerging from agents doing things together and then emerging, say, like an economy, or like in the case of a brain, concepts, or as we saw in the Wolfram article, talking about this computational irreducibility, that you can't reduce, say, like an economy to a set of plans. A planned economy is not going to be able to deal with a lot of the contingencies and a lot of the edge cases that you might encounter in the real world, whereas a bottom-up economy, a self-organizing economy does, that sort of thing. And there was a lot of that kind of work kind of early in that period of the mid-20th century, early 20th century, that kind of led us to, kind of the Santa Fe Institute brand of emergence. And so Hayek wrote this book, The Sensory Order, in 1952, where he proposed a framework for theoretical psychology based on the idea that the mind is a massive, interconnected system of pattern classifiers jointly possessing distributed knowledge that allows the organism to interact effectively with its environment. So this is kind of a very ecological psychology type approach. These ideas had clear affinity with his view of markets as distributed information processors. So the idea of free markets and self-organizing economies and things like that. This also, of course, influenced Will Wright, who built SimCity. SimCity's built on this sort of intellectual heritage, where no single individual or institution has complete knowledge of everything, and yet spontaneous order arises in the entire system through the interactions of individuals and their local idiosyncratic perspectives and objectives. In a way, Hayek's ideas anticipated the so-called system reply to John Searle's Chinese room thought experiment. Even if we grant that the person confined to the Chinese room lacks genuine understanding of Chinese, it would be much harder to argue about the entire system comprising 1. The person, 2. The rulebook for mapping queries in Chinese to appropriate responses in Chinese, and 3. The environment that supplies those queries and evaluates the responses insofar as it can maintain effective and coherent communication. So this is kind of like, this whole section is kind of like what Wolfram was talking about with irreducible computation, but also this idea that, you have to, you can have rules for something. You have your architecture, your network, which is the set of interactions, and then you actually have to run the program to get the behavioral output. You can't reverse engineer it. You can't even really predict it. You just have to run it and see what happens. So it is such as the case of a lot of generative systems and generative behavioral systems. You need to have, this, you don't necessarily have a genuine understanding of, say, like a language. You just generate the language based on the rules, and there you go. Even if the system knowledge of Chinese, sort of knowing how, could not be localized, it is there in a distributed form. Searle, who is a early cognitive scientist, who proposed this Chinese room problem as a means to say, whether something was really kind of cognitive or not. And this is kind of a distinction we kind of try to use between human brains and large language models. That is, some people would argue that large language models couldn't pass this Chinese room test, but human brains could. And so, that's kind of the difference in knowing how versus knowing what, or something like that. So this is, something that's contained in both large language models and minds, but also in minds you might have this sort of knowing what, or, having context that the large language model wouldn't. So Searle claimed that he could get around this by asking us to imagine that the person could memorize the rulebook, exit the room, and then just go on to simulate the system with its putative understanding of Chinese, still without any trace of genuine understanding. So, and then, however, we should go a bit deeper into how Hayek thought about the fundamental role of rules and abstraction. With all these ideas can be found in the sensory order, it is better to turn to Hayek's paper entitled The Primacy of the Abstract, which he presented at the 1968 Elbach Symposium. This symposium, whose theme was Beyond Reductionism, New Perspectives in the Life Sciences, had a lot of people who kind of thought about this. Conrad Waddington was there, Jean Piaget was there, Ludwig von Bertalanffy was there, and people who we have heard about from developmental psychology, developmental biology, from the complex systems of physics of complex systems, and people like that. And so the main thesis of Hayek's paper is that the primary characteristic of an organism is a capacity to govern its actions by rules, which determine the properties of its particular movements. That is, in the sense, its actions must be governed by abstract categories long before it experiences conscious mental processes, and that what we call the mind is essentially a system of such rules, conjointly determining particular actions. In the sphere of action, what I have called the primacy of the abstract would then merely mean that the dispositions for a kind of action possessing certain properties comes first, and the particular action determined by the superimposition of many such dispositions and comes later. So this is a very sophisticated view, positing a layered cognitive architecture, making use of abstraction or virtualization based on pattern classification. So this gets into a little bit about how he viewed behavior and some of these other things. Gestalt psychologists J.J. Gibson, Maurice Merleau-Ponty were all cited in here. And so this is sort of the intellectual trajectory he's taken on this. And then kind of going through his ideas about this. So this is consistent with sort of this idea of the Chinese room, and his view on the Chinese room is sort of in this way: the organism responds to, and thereby, as I like to call it, classifies the various effects on it of events in the external world. This is the limited extent in which it can be said that these action patterns are built up by expertise. It seems to me that the organism first develops new potentialities for actions, and then only afterwards does experience select and confirm those, which are useful as adaptations to typical characteristics of its environment. There will thus be gradually developed by natural selection a repertoire of action types adapted to standard features of the environment. Organisms become capable of ever greater varieties of action and learn to select among them as a result of some assisting the preservation of the individual or the species, while other possible actions come to be similarly inhabited or confined to some special constellations of external conditions. And so this actually influenced Frank Rosenblatt's thinking about the perceptron and about connectionism. And even Gerald Edelman, who wrote this book, Neural Darwinism, which talks about sort of his views on the brain and the mind, used this Hayekian evolutionary metaphor as well. So I think that's enough of that post. They're very good articles taken together. I think they really kind of, and I don't know if they challenge, but they definitely underscore this view of brain emulation and how we should maybe approach the higher order aspects of brain emulation, not just the connectome aspects.